episode of Science Max is all about liquids. What makes something float or not float?
Oh no! My loonies!
Liquid density and super absorbent gel.
Who wants to do an experiment with diapers?
Liquids. Today on Science Max, Experiment at Large.
Hey, welcome to Science Max Experiments at Large. I'm Phil McCordick, and hold on a second, I'm just gonna change. Okay, that's better. Now, where were we? Oh, right. Let's go make a boat. So you know that some things float and some things sink, like rocks, or wood, or full water bottles and empty water bottles, or carrots, foam, waffles, screwdriver, playing cards, plasticine, tinfoil, potato, my watch. Wait. That wasn't supposed to go in there. So how do you make a boat? You make it out of something that floats, right? Well, most boats are actually made out of metal. Tinfoil is metal and, well, it sinks. But if you fold tinfoil into a boat shape, it floats. And boats don't only float themselves, but they can hold people and cargo. In fact, there's container ships crossing the ocean at this very moment that are holding thousands of tons of cargo, and they're all made of metal, which doesn't float, it sinks. So how do boats do it? Are they magic? No, of course not. Boats are science. And here, you can be science maximites. Get some tinfoil and cut it into the same size pieces and fold a couple different shapes of boats and see which one can hold the most weight before sinking. And now it's time to max it out.
But before we do, here's how you can fold your own tinfoil boat in less than 15 seconds. First, take a square piece of tinfoil, then fold it in half. Fold one corner down and the other corner down. Then open it up and ta-da, you're done. If you want instructions on how to fold a more complicated boat, go to our website.
I have a feeling I'm gonna need a few extra lab coats for this experiment. Like I was saying, let's max out the tinfoil boat and find out a little bit more about why boats float. Okay, well, I'm here at an indoor pool, which is not, I wasn't expecting to be in the pool just yet, but this is where we're gonna build our giant tinfoil boat, so why not? Huznia.
Phil, you're wet.
I thought I was gonna come in over there, but I came in on the water sled. I think I had the coordinates wrong. Anyway, this is Huznia, and she's from Let's Talk Science, which is all about science education, right?
Yes.
Just like us. So you're gonna help me max out the tinfoil boat. I think I dropped it in the water. Hold on. Whoa! Here, where? There it is. The tinfoil boat. The tinfoil boat.
Phil, this is a boat?
Well, it looked a lot better before I came down the water slide, but that's the idea, and then we make it bigger. What do you think?
I don't think it's gonna work, Phil.
Oh, well, why not?
Tinfoil is very thin,
Uh-huh.
and it might not hold the shape of the boat.
Well, I still think we should use tinfoil, though.
Why?
Well, because the small experiment was tinfoil, and I bought all of this tinfoil.
Then let's do it.
Tinfoil?
Tinfoil?
Okay, high five. I'll take the tinfoil, and you take that, and I'm gonna have to dry off at some point.
Welcome to Shipbuilding for Pirates. I'm Swubby, and I've built some of the finest pirate ships for some of the finest pirates this side of the Caribbean. And I can teach you to do the same. But first, you need to know your basics. Mass and volume. Let's start with volume! But not that kind of volume. Which of these two chests do you think has more volume? Right, this one here. Which of these two balloons do you think has more volume? Right, this one here. Volume is how much space something takes up. Which of these two chests has more volume? That's right, they're the same. But which of these two chests has more mass? Which is heavier? Hard to tell, isn't it? But what if I told you that this one was empty and this one was full of treasure? Oh, loonies. Now, which one has more mass? That's right, this one. These two chests have the same volume, but this one has more mass. This chest has more volume than that one, but this one... My loonies! That chest does not have as much mass. Volume is how much space something takes up, and mass is how heavy something is. And when you look at them both together, you're looking at density. Join us next time on Shipbuilding for Pirates, and then we'll look at how volume, mass, and density work together to make something float. Oh, my precious, precious loonies. Are you all right, my pretties? They can't talk, so I'm not sure what they're saying.
So, Husni and I get to work constructing a large tinfoil boat. Our first design is just sort of a square, folded together out of a very large sheet of tinfoil. Simple, but can I ride in it?
There we go. A giant tinfoil boat, just my size. Woo-hoo-hoo-hoo!
I don't know if it's gonna work. It's too thin.
You think it's too thin?
I feel like yes.
What should we do?
Do you want to test it?
Let's test it. Okay, good idea. So here's the most important question. Do you want to test it or should I test it?
No, you test it.
All right, here we go. Putting it in. First test, does it float on its own? Yeah! Floats on its own, no problem. If I just get in very carefully, then it will work fine. See, if I'm careful about how I get in, no, it's fine. See, if I just get in like that.
Oh my! Bill, are you okay?
Wait a minute. It's sort of. No, that's just air. You know what went wrong? It wasn't boat shaped. I think if we make it look more like a canoe, because canoes float, if we make it look like a canoe, it'll work great.
No, Phil. We need some support. If we add a couple of structures in between, then we add support to it.
I'll tell you what. Let's make a boat like I want to make and a boat like you want to make, and we'll see whose is the best.
That's a good idea. Okay, let's do that.
All right, let's do it.
Welcome back to Shipbuilding for Pirates. I'm Swubby, and now we know what volume means, what mass means, and that together it can tell you something's density. Now let's find out why things float. Let's say we're out to sea and my treasure chest gets swept overboard. Oh no! But it's all right. It floats because it pushes enough water out of the way, displaces it to carry its mass. But what if my treasure chest had more treasure in it? Well, we're giving it more mass, but not more volume. Too much mass and not enough volume, and it will sink. Oh no, my loonies! You need more volume if you want to float more mass. And that is why things float. I'm Swubby, and thanks for joining me on Shipbuilding for Pirates.
So, the first version of the tinfoil boat didn't work out too well.
Like that.
But my idea is to build a tinfoil boat more like a canoe to see if a different shape makes any difference.
Tinfoil canoe!
Very Canadian.
Very Canadian. The canoe part, anyway. I don't know about the tinfoil part. So, Husni and I had a bit of a disagreement of why the last boat didn't work. I thought it was because it wasn't shaped enough like a boat, so this one looks like a canoe.
What I thought is that it requires some structure.
Structure so that it wouldn't fold together.
That's right.
And we'll see how it goes.
All right.
All right, here we go. Did it work?
Nope.
Okay, your idea next. Did you know It's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool. That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and half a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful. And you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out.
Ta-da! The longest length of liquid layers. 12 liquids all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really, really want to mix it up, but it took me a long time to make this, so I'm not going to.
Our first 2 attempts at a tinfoil boat haven't gone so well. Husnia's idea is to make a tinfoil boat and add some more structure, because the tinfoil just wants to collapse when I get in it. So we start with a large piece of cardboard on the bottom, then we wrap the tinfoil around it and shape it into a boat. After that, we add some supports across the top to stop it from folding in when we add my weight to it.
This boat feels a lot stronger than the one I was just in.
I told you.
So how does all of this work?
So we got some support using broomsticks and then some cardboard paper. And then underneath we have cardboard.
And so how will all of this help the boat not sink with me in it?
Right. The broomsticks will prevent it from folding this way and you won't sink.
Good.
The cardboard will prevent it from folding this way and you won't sink again.
Not sinking is my favorite thing to do in the tinfoil boat. All right, so let's try it.
Let's do
now,
it.
Are you gonna get in this one?
I'll tell you what, Phil. If you get in and you don't sink, I'll go after you.
Deal.
All right.
All right, here we go. It's sort of working. Oh no, water's coming in. It's sort of working.
It's almost working.
Uh-oh.
Wow.
No.
Hold on.
1, 2, 3, go.
Another thing I learned is that a very light tinfoil boat can be very heavy when it's full of water.
I don't know if fixing it is in the cards. I think we're gonna have to build another boat. So what do you think we should do?
Let's add more structure.
More structure?
Oh, yeah.
What if we add like a metal rod around the outside and maybe some more metal rods and ribs
and we wrap it all in tinfoil, and you think it'll work?
Let's give it a try.
Let's give it a try.
Don't worry about it. I got this.
No, I'll get it. I'll get it.
Sure.
Who wants to do an experiment with diapers? Oh! No, I'm serious. You may have a little brother or sister at home, which means you probably know where you can find some diapers. But there are two things you need to remember. First, ask an adult if you can use the diapers for your experiment. And two, only use unused diapers, okay? Okay. So, you take the diaper, and if you cut it, be very careful, maybe get an adult to help you, over some black construction paper, like I have here, and you shake the diaper over the construction paper, you'll see that there's a little powder that comes out. And this is the secret ingredient. This is super absorbent gel. And what it does is it soaks up all the liquid, and diapers are full of them. And you carefully pour it into a plastic cup, like that. Now you can see I have already done it with a number of diapers. It's important to use a plastic cup because it's a little messy, although it's non-toxic, it's totally safe, but it's still easier to clean up by just throwing the cup away. Now, add some water, and what happens is this super absorbent gel absorbs the water and turns very quickly into a paste. Look at that. Now, let's max it out. 5 kilograms of super absorbent gel, 500 liters of water. Now, it is time to do science! And I have my own stir stick. Yep, definitely coming along. I'm not exactly sure if we're getting anything on this camera, but I want to make sure it's recording. Yep, it's recording. There we go. It is definitely turning solid. Well, there you go. The giant super absorbent gel experiment. Corey, Trevor, I need some help getting out. How many outfits have I been through in this episode? How many outfits have I been through in this episode? Anybody have a towel? There you go. Thanks, buddy. That's great.
Husnia's idea of adding structure to the tinfoil boat was definitely right. We just needed to go further. So we did it again. This time, we made a much larger boat. We started with a sheet of cardboard, then wrapped the tinfoil around and added some metal supports taped to the cardboard across the boat this way to make ribs, as well as some other supporting pieces in the front and the back. Then another metal rod all the way around the top, and finally, supports across the middle.
All right, feel how strong it is. I'm really excited about this version of the tinfoil boat. What we did is we used thwarts, big hard pieces of wood that we did last time, but this time we have ribs.
Ribs, right, which are made of a cardboard, a metal rod attached to it,
and shaped, and we did a whole bunch of them that go the whole length of the boat. And then we used all of this bendable metal, and we have one that runs all the way around the gunnels, and a whole bunch that run down the inside, and we even used bike fenders at the front and the back of the boat to give it super rigidity so that it hopefully won't go like all the other boats have done so far. Are you ready, Husnia?
let's do this.
1, 2, 3, lift. All right, moving it over. It floats, but that doesn't tell us anything because they've all floated at this point. It's only when I get into it. Okay, here we go. All right. Hey! Hey, it works!
Whoa.
All right.
Oh, it's working.
Ha 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 ha! Look at that, it works perfectly. The tinfoil boat experiment has been done. Science Max, experiments at large. What do you think, Husnia?
The only reason I got into this boat because I knew it's gonna work.
Really?
Oh yeah.
So you knew you would never get wet? See, I don't think that's fair. I think it's time that you got wet. Yeah, I think we should go. I think you and I should just get wet right now. Just need.
Someone help.
You're still dry, aren't you?
Okay.
That is so unfair.
Science Max! This episode of Science Max is all about vibration and frequency. Frequency and vibration. What's the difference? We build a maxed out vibrobot, spin a giant disc, suspend water, and play with lasers. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites, and welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max Experiments at Large, we're going to be looking at vibration. Vibration is when things go back and forth, and back and forth. All kinds of things vibrate, like pendulums. Pendulums. Wait, and pendulum. Pendulums are designed to swing back and forth. Stop that. Also, metronomes. Metronomes are used by people when they're practicing music to keep accurate time. Yeah. Okay, putting it back. And okay. We're gonna be building. Whoa, okay. We're gonna be building this little guy. This is a vibrobot, and he vibrates and he skitters around on the paper. And if we take the caps off the markers, he makes interesting patterns on the paper. Okay, so let's get started. Let's build a vibrobot. Okay. Oh yeah, you know what? Maybe it's time to take off the ski boots, huh? Whew. There we go, that's better. So today, like I said, we're gonna be making a vibrobot. And here are all the materials you need to make your own. Plastic cup, 3 markers, an electric motor, just make sure you ask an adult first, a battery, a plastic drink bottle cap, a toothpick, scissors. This kind of tape is called electrical tape. Science tape, which is the same as invisible tape, but of course I use this tape only for science. And some modeling clay. And these are 2 bendy straws that I've taped googly eyes to. These are not necessary. I just like them for decoration. Now remember, if I'm going too fast here, which I probably will be, you can get all of the steps on how to make your very own vibrobot on our website. Okay, so here's how you get started. First, you're gonna make the feet for your vibrobot. So I attach some science tape to the markers, and then I put the marker on the bottom of the cup. And then I do that again to the next marker, and then the third, balance it like that. There. Next thing you wanna do is take your plastic drink bottle cap and make a hole with a toothpick. You wanna make it off to the side, right about there. Just like that. That's so when it turns, it will be off center. That's what's gonna give us our vibration. So once you've made that hole, take some modeling clay and stick it in the cap to give it some weight. When you've done that, stick it onto the shaft of your motor like this. See how it's off center there? Now we just need to attach it to the vibrobot. I just put it right here on the top, and I like to attach the battery to the back of the cup. And now finally, we're going to attach the eyes. We take some science tape, and we put the straws over here. I am vibrobot. I am here to vibrate. Take me to your leader. So then you attach your tape with the wire to the top of the battery there, and then the other wire to the bottom of the battery, just like that, and let your vibrobot make some art. Ha 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 ha. Now, if the battery is new, your vibrobot might be jumping up and down quite a bit. So you can do what I like to do and add some more weight, and then you make better lines with your vibrobot. And your vibrobot makes art. How long will he last? Probably till lunch. And there you go. Vibrobot art! Art made by a robot. How cool is that? So that's what we're gonna do today. I'm gonna meet Chris from Logix Academy, and he's gonna help me max out the Vibrobot. Plus, we're gonna learn a little bit more about vibration. Come on. Oh, hey, Chris.
Oh, hey, Phil.
Thanks for coming.
My pleasure.
Okay, here's your Science Max lab coat.
Thank you.
So you guys at Logix Academy, you also build a Vibrobot, right?
That's right, we do.
This is mine, and it works pretty well.
That's awesome.
So, I want to max this out.
Cool.
So I thought we would start with, instead of this motor, we would start with this motor.
Wow.
It used to be a round circle, but I cut it off so that it's off-center.
Perfect.
I've also got, this is our battery.
Fantastic.
That's as far as I've gotten so far.
Well, it looks like we need a frame next.
Right, something to be the cup.
That's right.
So we just need some sort of larger cup.
Ooh, how about that metal shelf over there?
Oh, this thing?
Yeah.
This is just something I keep my parts on.
It's perfect.
Really?
Yep, the shelves will house everything that we need, and it looks like it'll be strong enough to hold everything together.
Now, the Vibrobot had markers on the bottom of it.
That's right.
To make a little pattern. Should we try that with this?
Because we're going bigger, what if we used paint and paintbrushes instead?
Okay, sure. We could attach paintbrushes to the legs. Pass me one. All right, so now all we need to do is get some paint and some paper.
That's right.
And we can fire it up. Okay, let's move it over this way.
Vibration and frequency. What's the difference? They're all connected. Ta-da! Now, whoa. Vibration is things going back and forth. Back and forth. And back and forth. It's a cycle. Cycle, 25 bucks. Oh yeah, it's the wrong kind of cycle. Never mind. Well, if that's vibration, then what's frequency? Well, frequency is a measure of how fast or slow, how frequent those vibrations happen. Look at this bowling ball. Look. It is swinging back and forth, but not very fast. You could say it has a low frequency. We measure all kinds of things by the frequency. This thing is terrifying. When you turn the dial on your radio, you're tuning in to different frequencies of radio waves. Hey, look at this punching balloon. It's going very fast. You could say it has a high frequency. So, now you know. Vibration is something going back and forth, and frequency is how quickly it does it. Ramona, the bowling ball keeps coming through everything. How do you turn it off?
Okay, back to our main experiment. Chris and I are taking a Vibrobot and maxing it out. We have a large motor and a battery, and we're taping it all to some shelving. Just like our small Vibrobot, our motor needs something to make it unbalanced when it spins. That's what will cause the vibrations.
It's just taped. I haven't attached it in any other way. Do you think that's okay?
As an engineer, I have superior faith in duct tape.
Okay, well, that's good to know.
We're also adding an on-off switch and some paintbrushes on the bottoms of the legs so our maxed out Vibrobot can make art just like the small one. The final step, dipping the brushes in paint and setting it on a big piece of paper. We fire it up and it immediately shakes everything off the shelves.
It totally spilled all the stuff on the shelves.
The motor shakes the Vibrobot a lot. But there's a problem. All that shaking is starting to take its toll on the shelves. The wheels come off, the screws come out, and finally...
Whoa. It totally shook itself apart.
Destroyed itself.
The shelving unit just completely falls apart when it's being shaken.
Vibration is really hard on the structure of an object. We need something more sturdy, something that can take weight.
Steps, maybe?
Yeah.
Okay, hold on.
Okay.
Okay.
Yeah, this looks much better.
Okay, great. So we build the new Vibrobot out of this. So more paintbrushes,
Bigger motor, more paint,
more everything.
more everything.
All right, good. This is a pendulum. It's just a weight suspended on a line and anchored from above. Pretty simple. Pendulums were used for hundreds of years for all kinds of reasons, but most famously in clocks. Why were pendulums used in clocks? Well, here's why. Let's mark every time the pendulum hits the bottom of the swing, right here. Okay, watch. All right, now here's the question. How fast will the beeps be if I swing it from much higher up? Let's find out.
No matter how high the pendulum swings, it keeps the same frequency. That's why they were used in clocks, because it could swing for a long while, and even though it would lose energy, it would still keep perfect time. The frequency of a pendulum doesn't change, no matter how high it swings or how much weight is on the bottom. The frequency comes from how long the line is.
Now this is a pendulum wave.
Because each bowling ball has a line that's a different length, they have a slightly different frequency. They start out swinging together, but soon they start to make interesting patterns. Remember, each pendulum is keeping its own perfect time, even if it's slowing down. It's only the length of the line that gives each pendulum a different frequency.
And now we're gonna max it out with well, I guess these are already bowling balls, so this is already pretty maxed out. I'm just gonna leave that there. These are balloons. This is a laser, and these are awesome laser safety glasses. Now, lasers are made of light, and light has a frequency. In fact, each color of light has a different frequency. This is a red laser. Check it out. Yeah, cool. This is also a very powerful laser. Oh, I can pop the blue balloon with the red laser because the blue absorbed the red light from the laser and then it heated up and the balloon popped. But here's the cool thing. I cannot pop a red balloon with a red laser because the red balloon reflects the red light from the red laser and I can't pop it. If I wanted to pop a balloon with a red laser, I need to use a darker balloon, one that absorbs the red light, like a black balloon. So there you go. Lasers, frequencies of light. I'm gonna keep this red balloon because it's always nice to have a balloon.
Chris and I are maxing out the vibrobot, but our last version shook itself apart. Now the plan is to start with something more solid and try again. We found some very solid steps and added an even bigger motor, an even bigger battery, and attached a half-circle wheel to make the vibrations when the motor spins. We add some paintbrushes and fire it up.
Here we go! Come on!
Go, vibrobot!
It wants to move.
Is it moving at all?
So it's still not working. It's sort of getting caught in the paper and it's on the paintbrushes.
And the paintbrushes seem to be absorbing too much vibration, and then the paper's stopping it as well.
So why don't we remove the paintbrushes?
Yeah.
And we might as well remove the paper if we don't have any more paintbrushes.
Yes.
And we'll see what happens.
We'll see what happens.
Okay. No paintbrushes, no paper.
Okay.
Now let's try it. 3, 2, 1, go!
Yeah! Aha! It's moving. Not bad.
The shaking is good, but I don't know if the shaking is enough. So what do we do?
Well, we could add another battery.
Another battery which would give it more power?
That's right.
Okay, let's try that.
Okay.
Okay, so it wasn't working before,
No.
not enough power. And now we've got a second battery here.
That's right. We've wired them up so that one power feeds into the other, so we've got twice as much juice as we did.
So it's just a matter of clipping this onto there.
That's right, but hold on.
Yeah, safety glasses, because now we don't know what's going to happen anymore. Ready? 3, 2, 1.
The extra battery makes a big difference. The new vibrobot shakes around and only shakes itself apart a little.
All right, that was amazing. Okay, so all we needed was more power.
That's right. I think it didn't have enough power to vibrate up and down, and that's why it wasn't moving every time it hit the ground.
So I think if we're gonna use this much power, I think we need to build it again.
Okay.
Build it even stronger and with a bigger motor
Yeah?
and more power. And then maybe I ride it.
You think we can build that?
Of course.
Of course. Okay, let's do it. You want to see something cool? I can make this water levitate, defy gravity using the power of science. You want to see? Behold! Gravity-defying water! I can even make the water go very slowly. Or I can make the water go back up into the hose. Or I can make the water completely stop. You know what's interesting? The water does not seem to be stopped for me. You see stopped water because you are looking at it through a TV camera. See? Real life, TV camera. Real life, TV camera. You see, movie cameras and TV cameras take a whole bunch of still photos and then run them together really, really fast. 24 times a second for our TV cameras. I have created a device that drops water at 24 times a second, and what happens is everything lines up, so it looks like the water drops aren't moving. But watch this. I grab the hose and it's fine. But I let it go, and the hose is vibrating back and forth at exactly the same time the camera shutter is going back and forth, and everything looks like it stopped. The power of frequency has defied gravity. Okay, so not really. It's kind of a camera trick, but I prefer to call it science.
Here's a fun way to play with things going back and forth. This is Euler's disc, and it's designed to spin like this. What's going on is friction and gravity are slowing that down and pulling it towards the Earth. Now, you don't need a fancy disc like this to do this at home. All you need is a pot lid. Check it out. When the pot lid spins, friction and gravity start to slow it down, which means each spin gets lower and lower, and the frequency gets higher and higher. But the difference between a pot lid and Euler's disc is Euler's disc is made to go for as long as possible. The heavy puck has a slightly rounded edge and sits on a glass surface that is slightly concave, like a bowl. All of this is designed to make Euler's disc last a really long time, which is quite a while. But eventually, friction and gravity pull the disc down, and finally, it stops. Pretty amazing, right? Well, wait till we max it out.
This is Trevor, head of the Science Max build team.
Hey.
Thanks for setting this up, Trevor. So what is this?
This is a giant side of a spool, big hydro spool.
Okay, so this is the largest disc that we could totally find, and we've got it all hooked up here. We lift it up, we spin it, and then you pull the thing and it will drop down and spin like a coin, because it's the only way we can do that with something this heavy.
Yeah.
Ready?
I'm ready.
Okay.
Trevor and I hoist it up and get it suspended above the ground. Then I start to wind it up.
Ready?
When it's going fast enough,
And go, Trevor!
Trevor pulls the release and it turns out a 200-kilogram spinning disc works exactly the same. As it spins and rolls, gravity and friction work on it, and the frequency speeds up as it gets closer to the ground until it stops.
Giant Euler's disc. Nicely done, Trevor.
That was awesome.
That was great. Let's do it again.
All right.
Our vibrobot was working well, so that means it's time to make it way bigger. We started with a big metal table and added a huge motor, one 20 times as powerful as the last one. Instead of batteries giving us 12 volts of power, we're going to use a plug, which is 10 times more power. We've added an off-center wheel for vibration, bolted the motor to the frame, and added a protective cage all around to prevent anything from flying off. It even has a seat for me to ride.
Okay.
Okay.
You ready?
Ready?
Here we
We
go.
fire it up and it's very shaky.
Oh, wow. Wow. That was really uncomfortable. It was like very bangy, even with the seat.
Yeah.
I'm gonna try standing on it.
All right.
When I try standing on it, the vibrobot lives up to its name. It vibrates all around the lab.
Oh, wow. My legs are numb to the knee.
I'm not surprised.
Vibrobot!
All right.
Yeah, that worked really well.
That was awesome.
I really can't feel my feet right now. And it held together, which is impressive.
That's right. The more power and the stronger structure paid off.
Yeah. The only thing I regret is not getting a chance to... Wait a minute, come with me! Okay, so I achieved my dream of riding the vibrobot.
You did.
But we never got a chance to make art, so we've dipped a whole bunch of nuts and bolts and heavy things in paint.
Yep.
And now we're gonna turn on the vibrobot and see if we can make some art. Let's see how it looks.
Oh, wow.
Ta-da! Vibrobot art. Vibrobot has been a huge success, and we got some art to keep. High fives. Well done. Science Max, experiments at large. Who gets to keep the art?
Rock, paper, scissors.
Okay. 1, 2, 3. Okay, tie. 1, 2, 3. Tie. 1, 2, 3. 1, 2, 3. Wow. 1, 2, 3. Ah, tie. 1, 2, 3. Man.
Science Max! Today we're looking at polymers.
Polymers. Word has lost all meaning.
Plastics, latex, rubber, and our favorite polymer, slime.
Oh, yeah.
All on this episode of Science Max, Experiments at Large.
Oh, greetings, Science Maximites. My name is Phil, and I think I might have overdone it with the science. I mean, what's a better use of science than creating a whole bunch of slime? Well, I did, and you know what? It's really cool. Slime. I love slime. It always makes me feel like a mad scientist, but I need a good mad scientist laugh. Yeah, it needs work. Anyway, today we're talking about polymers. Polymers like slime. But you see, polymers aren't really a substance. They're more how something is constructed. And there's all kinds of different polymers. There's slime, obviously, and rubber polymers, like rubber. And there's also hard polymers like plastic. Now, polymers are all kind of constructed the same way. Like this. This is a chain. Yeah, so imagine this is a chain of molecules, and all the molecules are the same, and they just repeat in a long line. Now, when you get a polymer like slime, all the chains are not connected or very loosely connected, which means that they can flow over each other like a slime or sort of like a liquid, and they behave like that. So that is slime. But when you get to a rubber polymer, you start to get little bonds in between the chains of polymers that work like this. You see, they still move around a little bit, but they can spread apart, and they become flexible and bouncy. Yeah, I know, a chain doesn't really bounce, but rubber polymers do. Huh? Now, when it gets to a solid polymer like plastic, there's a lot more links, and it's all kind of interconnected, and it doesn't move at all. It doesn't move. Okay, again, harder to tell with a chain, but plastic is very hard and rigid. So let's dive into the world of polymers and make some slime. Yeah, too mad, not enough scientist. I'll keep working on it. Anyway, to make slime, take your white glue and pour in an amount. It really kind of depends on how much slime you want to make. Now, you want to add about twice as much water as that. Yeah, somewhere around there. Great. Now we want to put in just a little bit of soap. Maybe there, that's good. And you want to put in your food coloring. I like green. Green seems like the right slime color to me. It's the right appropriate mad scientist kind of slime. And then you want to start mixing that up till you get the right kind of consistency. That means make sure the glue and the water are equally mixed up. Good. And now we're ready to make it an actual slime by bonding the polymers together by adding liquid starch. Very good. And you want to mix it up. When you add the liquid starch, it starts to bond the chains of molecules together, changing it from a liquid to a slime. It's coming along. And there you go, slime. Now, if you want clear slime and not opaque slime, you want to use clear glue and not white glue. But that's basically the recipe. So there you go, slime. Too supervillain? Yeah, okay, well, anyway, all right. Now all you need is an expert to help me max it out. Of course, my interface is hand gesture based, so I don't know if the slime, oh, hey, there we go. Great, so you get it, oh, of course, Sarah from Mad Science. Mad Science, they really know their slime. This is great. Okay, I got it close. Hey, there we go. All right. Ugh. I'm not sure if bringing it through the portal is such a good idea, but at least I'll have it on the other side. Ugh. I have a pot. Why do I have a pot? I didn't have a pot when I went through the portal. Is someone somewhere missing a pot, or did it just create this pot out of nothing? Huh. Hey, Sarah!
Hi, how are you doing?
Good, Sarah from Mad Science, you're gonna help me make some slime.
Yes, I actually brought some. Oh, this isn't slime. This is a pot lid.
Hey.
Oh.
Well, at least we have a set. Doesn't answer any questions, though. And I guess we're gonna have to make some more slime.
Definitely. What kind of slime do you want to make?
What do you mean, what kind? Is there more than one kind?
Oh yeah, there are tons of different kinds of slime with lots of different ingredients and recipes.
Oh, I only know the one. Can you show me all the others?
Of course, let's go make some right now.
Okay, great.
Awesome.
Come on down to Sal's Science Shop and see me, Sal, while you shop for science. This week only, Sal's one-of-a-kind, once-a-year polymer sale. 50 to 75% off anything made of polymers. Rubber? That's a polymer. Polystyrene. When you're eating your next meal, I recommend some polypropylene. Low-density polyethylene. High-density polyethylene. You want some polytetrafluoroethylene? We got it. We've even got polychlorotrifluoroethylene. Do they even know how good a deal this is? Because you're not gonna find that kind of deal just like every day. But hold the phone. Polymers aren't just plastics. Rayon, nylon, Teflon, you name the lawn, we got it on sale. What do we want? Polymers. When do we want them? Anytime during normal business hours. Wool, silk, even cotton. Polymers, polymers, polymers. Polymers, polymers, polymers. Word has lost all meaning. Glue, paint, umbrella fabric, oh yeah. Carpet, you bet that's on sale. Roberta, I'm running out of sale signs. Buy it and I'll put it in a plastic bag, also made of polymers. Seriously, Roberta, we can't have a sale on everything. Oh, hey, even you, even me, the proteins in our bodies, even our DNA, all polymers. So come on down to Sal's Science Shop and get a great deal on your polymers for a limited time. I mean, it'd have to be a limited time, right, Roberta? Because, I mean, I can't discount everything in the store to 75% off. How am I gonna make any money? I mean, are we still rolling? 100 different kinds of slime.
Yes, it's gonna be so much fun, but we're not gonna make 100 today.
Yeah, I know. We're just gonna do our top favorites.
Yeah, it's gonna be super great.
All right, what are we starting with?
So our first slime we're starting with today is some really cool molding slime. Now this slime, actually, if you leave it out overnight, it'll harden and you can make an imprint of whatever you like. So here, we made an imprint of our little tool there. So we're gonna look at a little bit more liquidy slime, starting with this one over here, which I believe you already know about.
This is cornstarch mud.
Exactly.
You hold this.
Sounds
I'm gonna
good.
hold this and we're gonna try pouring it. Whoa,
Whoa.
So, see, it's like a liquid, but then if you do it fast, it's like a solid. All right, what's next?
Over here, we have some other really awesome types of slime. So right over here, we have some crunchy slime.
Crunchy slime?
Exactly.
Why is it crunchy?
Now it's crunchy because we've actually added a few beads inside of it to make it crunchy. So this is some really cool, awesome slime.
Here, you take half.
And you can feel the beads as you stretch it out. It's so cool.
This one is a little harder to clean.
Exactly.
I'll just do that. All right, so what's next?
So next we have some really cool glow-in-the-dark slime.
Glow-in-the-dark slime.
Yeah, it's so awesome.
Ooh, look at how much it glows. That glows a lot. That's super glowy slime. So to do the different kinds of slime, we need the polymer.
Yes,
And then the thing that sticks the polymers together.
exactly.
So the glue is the polymer.
Glue is the polymer.
And the starch is the thing that bonds it.
Yes,
Aha.
very cool.
And then you put the thing in that makes it the kind of slime.
Yes, right before you add the bonding component, because if we keep adding stuff after it's already made, it unfortunately won't be able to take it. So we add our powder before we add our starch in this situation.
Should we go on to the next thing?
Yeah, let's move on to
More slime! Plastic is great, and plastic is everywhere. But the problem with plastic is it isn't very biodegradable. It doesn't break down in the environment. I'm still on hold. Oh, well, there you go. Back for another couple years, I guess. But here's a way that you can make bioplastic. It's fully biodegradable because it's made of natural materials.
The recipe is easy. 2 parts cornstarch, 3 parts water, a few drops of cooking oil, and some food coloring to make it whatever color you want.
Purple, science purple.
Mix it up and it turns into a paste.
Now what you'll need are 2 things. 1, an adult, and 2, a microwave.
Put it in for 30 seconds.
Clock wipe. There we go.
Then take it out and mix it some more until it cools down. Then you can pull it out and use your hands to sculpt it into a shape or take the shape of something else.
Once you put it all the way around, you can turn it into a little flower pot.
Once you've sculpted it,
You need to wait for it to dry, which will take about a day. Clock wipe.
after waiting a day,
Huh? What? It's been a day? Oh.
you have something made out of bioplastic. Like this little flower pot you can use to grow a small plant.
And then when it grows big enough, you can take this biodegradable flower pot and plant it right outside in the dirt, and this pot will biodegrade and turn back into dirt. Pretty cool, right? Well, let's max it out. Biodegradable frisbee! Check it out! It's a frisbee, but it's biodegradable. So you throw it around in the park, but if you lose it, it turns back into dirt. Ha-ha! What, not enough? Okay, clock wipe! Biodegradable lawn chair! Use it for 1 season and then return it to the earth afterwards. I think this is one of my best Science Max. Okay, bioplastic lawn chair not as strong as regular lawn chair. We've learned that lesson now, so that's good to know. I mean, how would I have known if I hadn't tried it?
Sarah and I are looking at different recipes for slime.
All right, what do we got here?
So over here we have some amazing foamy slime, which has so many ingredients in it. Here, watch what happens when we start pulling it out.
Ooh, wow. So it's like,
Super stretchy and super fluffy.
here, that's great. Okay, now you gotta hold yours. You gotta hold this end. Okay, and then take some more. And then we take that. And then, yeah. It gets thinner and thinner and it becomes more and more lines of foamy slime.
Yeah. And the last kind of slime we made today is some classic Flubber slime.
Ooh.
So much fun.
Now, why do you think is it Flubber slime? Because is it really a slime?
It is a slime, yeah. It's super fun and it's super stretchy.
Oh, okay, I get it. Look at that. And it's sort of like a little bit like gelatin.
It is almost like gelatin.
Here, you can have some. There you go. Whoa. Ah, whoa. All right, so Sarah, now what we need to decide is how we're gonna max it out.
Right.
Like, should we just get a lot of slime?
That sounds like a really good idea, but we are gonna need something to put it in because we can't just have slime all over the floor.
Okay, you're right. So we'll get some sort of container thing.
Yeah.
And we'll see how much slime we can make, and then we'll just play with it and see what happens.
Sounds good.
And yeah, we will experiment because it's science.
Yeah.
Okay, high five. Careful high five so we don't splatter. Okay, good. Okay, let's go. This is right.
This is a rubber glove. Well, actually, it's a latex glove. What's the difference? I will get to that in a second, but I'm sure you can agree it's super stretchy. How stretchy? Let's fill a rubber glove with water and see how big it gets.
So, difference between latex and rubber. Well, it all comes from a rubber tree. Well, actually, it's a fake tree. It's just to show you how it works. The sap of the rubber tree is collected just like this. There's a spigot, and then the sap goes out and it's collected. It's the same way that the sap for maple syrup is collected. And this is natural latex. If it's dried out, it becomes natural rubber. Latex generally means the liquid form, and rubber means the solid form. But wait, then why is this a latex glove? The glove is not liquid. What's the deal? Well, generally, latex means water-based or liquid, like latex paint. But it could also mean synthetic latex. That's latex that's man-made and doesn't come from a rubber tree. So, we call rubber gloves because they used to come from rubber trees, but now they're usually made out of man-made latex. But either way, they're super stretchy. I wonder how big this is gonna get. Science! Sarah and I are maxing out polymer slime. How? Maxed out tub of slime! Whoa! Okay, so how do you feel? Are we mixed up enough? First, we mix up a bunch of slime in a garbage bin. So with the polymer chemistry, the polymer is generally a liquid, right?
Yeah.
And the bonding agent makes it stick together. So the more we use, the more of a solid we get.
Exactly, yeah.
So we want to split it and make it sort of halfway between a liquid and a solid, and I think we're exactly at the right stage.
It looks perfect.
Oh, yeah. Okay, so let's dump this garbage can in.
All right.
All right. Then we dump it in.
Oh, gross.
Whoa. Turns out we needed more slime. I don't think that's gonna be enough.
I think we might need some more slime.
Yeah, how much more do you think we need? So, we added 11 more. Ah, delicious. Last one. Oh, yeah. Then we experimented. Oh, yeah. We have a giant tub of slime. Because the slime is stretchy, it created amazing bubbles. So do you think I could blow a bubble with the slime?
Well, maybe not you, but
Do I
definitely
wanna
the air
try this?
compressor.
No, no, I'd have to just put it on my face. I think I've already got it on my face. Then there was only one thing left to do. We get in the slime.
Can we do that?
We can totally do that. This is science math.
That's so exciting!
Going swimming in slime!
Yes!
Who's going first?
You are!
I am, obviously. All right, this is how Science Max does polymers. 3, 2, 1. Plastic is everywhere, but what can we do with it aside from recycle it? Well, we can reuse it to make cool plastic charms. But you're gonna need the right kind of plastic, and you need polystyrene. Just look for the little number 6 inside the recycle symbol. Cut out some plastic and decorate it however you want. There we go. Haha, check it out. The Science Max logo. Also, I've made a couple other things. I've got a chemical symbol, an atom, and this is me in some slime. Then get an adult to help you put it in the oven or toaster oven at 350 degrees. It only takes a few seconds for the plastic to shrink to 1/3 its size. The reason why this happens is when plastic is manufactured, it's heated and stretched out and then cooled, and it sort of freezes in that stretched out shape. And when you reheat it, it shrinks back down to the unstretched shape. Get your adult to take it out and wait for it to cool, and you'll have yourself some small plastic designs you can use for keychains, bracelets, name tags, bookmarks, whatever you want. All using the power of polymers. Awesome, I'm gonna make all of those. What was that again? Keychain, ornament, magnet, magnetic putty in 60 seconds. This is magnetic putty. This
is magnetic putty.
10 take.
This is magnetic putty.
26.
This is magnetic putty.
2,635.
This is magnetic putty.
I can't count this high.
This is magnetic putty. Magnetic.
Oh, it's not a magnet. It's attracted to magnets. Oh, that makes more sense.
This is magnetic putty, and this is a magnet. The putty is made of polymers, which means it can flow over itself. It also has lots of iron filings in it, which is why it's attracted to magnets.
This is what happens over several minutes.
And there you go, magnetic putty.
Okay, so where were we? Oh, yeah.
3, 2, 1, yeah!
And remember, don't try this at home.
Slime!
Sarah and I enjoyed our maxed out tub of slime. So let's recap. Slime is made of polymers. Polymers come in a lot of different forms. It's all about long chains of molecules. And none are more fun to swim in than slime.
Do I have slime here?
Ooh, yeah, definitely.
Slime here! Slime! Well, there you go. Science Max experiments at large. Polymers. Slime. Yeah. High fives. Yeah. Slimy high five. Yeah.